Let's wrap up all of Chapter 6 at the same time. After Section 6.1, you should be able to interpret sample standard deviation and quartiles of a quantitative variable, and use stacked box plots, histograms, or dot plots to determine which of two groups had a higher mean or median, or had a higher standard deviation or IQR. You've practiced these quite a bit already, and even had an exam question on them. Review the preliminaries PowerPoint and descriptive stats worksheet under Day 1 content for more review. From Section 6.2 and 6.3, we've added quite a bit. For data with one categorical and one quantitative variable, you should be able to define the parameter of interest, write the null and alternative in words and in notation, describe how to use cards to create one simulated sample which assumes the null is true, interpret a p-value in context, calculate and interpret the standard error of the difference in means, calculate and interpret a standardized statistic, check validity conditions, use a p-value or standardized statistic to draw a conclusion about an alternative hypothesis, and calculate and interpret a confidence interval for a difference in means. We'll work through an example from the textbook to make sure we understand each bullet point. Section 6.2 presented an example about bicycling to work and seeing if bicycle weight will affect commute times. An experimenter for 56 days tossed a coin to decide if he would bike the 27 miles to work on his carbon frame bike, which was lighter than the steel frame bike. For each trip, he recorded his commute time. What are the observational units here? The 56 days. Think about our sample. We have a sample size of 56, or 56 days, and therefore days, or each trip, is one observational unit. How about the explanatory and response variables? The explanatory variable would be which bike he rode, or the weight of the bike frame, steel or carbon. The response variable would be the commute time. Notice each variable here, explanatory and response, is measured on the observational unit, the day. What would the parameter look like for this example? Well, since we're working with one categorical and one quantitative variable, our parameter will be the difference in true means. In this context, the difference in true mean commute times between the steel and carbon frames, represented as μc minus μs. Notice I don't have a value here because I don't know the value of the parameter. How about the null hypothesis? The null hypothesis is always that there is no difference in the true means. In this context, no difference in the true mean commute times between the steel and carbon frames, or μc minus μs is equal to 0. For the alternative hypothesis, all I'm wondering is if there is a difference in the true mean commute time between steel and carbon frames for this research question. Notationally, μc minus μs is not equal to 0. Here we see the raw data. Looking at the stacked box plots and dot plots, how would you describe the two distributions? Both look roughly symmetric, though you might argue that the carbon distribution has a very slight right skew due to the long right tail. The medians look similar, but the variability is larger in the carbon data. How about the notation for each value in the table? If we use the same informative subscripts as before, C for carbon, S for steel, we would have N sub C equals 26, X bar sub C is 108.34, S sub C is 6.25. N sub S is 30, X bar sub S 107.81, and S sub S 4.89. Therefore, our observed statistic is X bar C minus X bar S, or 108.34 minus 107.81, which is equal to 0.53 minutes. You absolutely could reverse this order of subtraction. You just have to be consistent with the order of subtraction throughout the problem. Here we see the original data separated by group. In a test, we must assume the null hypothesis of no difference in true mean between commute times. Therefore, in our simulation, we want to ignore what group, or type of bicycle frame, an observation came from. So, we'll write the response times on 56 cards. We'll shuffle and deal those cards into two stacks of the same size as the original groups, 26 in the new carbon group, 30 in the new steel group. Then we'll find the difference in means for this new grouping and plot that value. Let's see that again. Find the new means in each group and we plot the difference between them. Just a third time because the animation is fun. Shuffle the groups without changing the response times, find the difference in means, and plot that value. We'll run and repeat this many times to develop a null distribution. Here you are seeing a null distribution with 30 simulated samples. We call the observed statistic was 0.53. Because the test is two-sided, we need to count values farther in the tail than 0.53 on either side of the null value. So since the null value is 0, that means we will count the number of simulated differences in means at or above 0.53 and at or below negative 0.53. For this distribution, our p-value would be 19 out of 30 or 0.63. If you were to do this with 1,000 simulations, which is really what we should be doing, not 30, you should get a p-value of about 0.72. How would I interpret that p-value, or what does that p-value mean? We could say if the mean commute times for bikes are the same in the long run, that's saying the null hypothesis is true, and we repeated random assignment of the lighter bike to 26 days and the heavier bike to 30 days, a difference as extreme, the alternative, as 0.53 minutes, the observed statistic, or more, would occur in about 72%, the p-value, of our repetitions. Now let's think about a conclusion. We do not have evidence, because our p-value is large, that the commute times for the two bikes will differ in the long run, that the alternative is true. What if we would like to use a theoretical approach instead? Is the validity condition satisfied with these data? Yes. Both distributions are roughly symmetric. Or, if you want to say that the carbon distribution is slightly skewed, you could argue that the steel distribution is symmetric, and though the carbon distribution has a slight right skew, the sample size, 26, is greater than 20, so the validity condition is met for both groups. Let's go ahead and calculate the standard error. The standard error of the difference in means will be s1 squared over n1 plus s2 squared over n2, square root of that whole piece. In your calculator, you should get 1.516. How would you interpret that value? On average, each difference in mean commute time between the two frames is 1.516 minutes away from the true difference in mean commute times. Now let's calculate our standardized statistic. Our t-value will be the observed difference in means, 0.53, divided by our standard error we just calculated, 1.516, to get a t-value or a standardized statistic of 0.350. How would I interpret that? The mean carbon frame time of 0.53 minutes more, or longer, than the mean steel frame time is 0.35 standard deviations above the null value of no difference in means. Now let's do a confidence interval. In a 95% confidence interval for these data, we would tell you to use 2.060 as the multiplier. The standard error formula for a difference in means is the same for a test and for an interval. So to find my 95% confidence interval, I would take my observed difference in means, 0.53, plus or minus my multiplier, 2.060, times my standard error, 1.516. And you should get an interval of negative 2.59 to 3.65. How would you interpret that? Again, make sure you include order of subtraction. So I could either say, we are 95% confident that the difference, carbon minus steel, in true average commute times is between negative 2.59 and 3.65 minutes. Or I could tell which group is higher. We are 95% confident that the carbon frame bike is between 2.59 minutes faster, because the sign is negative, to 3.65 minutes slower, positive, than the steel frame bike on average for the population of commutes. Let's think about scope of inference. Can we generalize the results from this study? No. The experimenter commuted on consecutive days from January through March, which didn't include all seasons, so this is not a random or representative sample of commutes. Can we conclude causation? Yes. He flipped a coin for the bike, making this an experiment which used random assignment, and therefore cause and effect conclusions are valid in these data.